So we'll start just to not be too late. So our next talk is going to be given by Benoit from the University of Waterloo, and he's going to talk about well, its talk is called Me plus U plus interactive proof.
Hey everyone, we're going to speed it up because it's going to be fast, but we're going to start with an example. Set theory, if you remember your axiom of separation, let D be the set of all beverages, L the set of all drinks that are not Coke. So I have one drink that is Coke, and one drink that I'm not sure whether it's not Coke or not. And I need someone to help me, because it's an interactive proof. Does anyone among us think that they can suss out whether a given drink is Coke or Pepsi? I see a lot of people, 1, 2, 3, 4, 5, 6, that want to help. I'll pick this lovely young person. I have two prompts, well, 4 prompts. Do you want to come up?
Okay, sure.
You can introduce yourself to the world. We get a round of applause. I'm going to open these two. Okay. And I'm not sure whether they're the same thing or not. But if they're truly different, you should be able to distinguish them. I don't have a tongue, so I can't do it. But what I'm going to do is you're going to turn around. Okay. I'm going to flip this coin, this 1 peso. And if it comes up head, I'll pour in this Coke. If it comes up tails, I'll pour in the Pepsi. I can give it to you, you're going to tell me. Okay. If you fail the test, then I know that you cannot distinguish them perfectly. And I know that if I need to show that they're different, I have to go ask someone else. If you pass the test, I only have a 50% probability. You could have gotten lucky. So I'm going to repeat this test 3 times. So that if you pass it all 3 times, there will be a 7/8 chance that you can indeed distinguish these, and 7/8 is good enough for my life. So here we go. And this result is a secret for now, but the audience will be able to see. Okay,
now
so
the pressure's on.
Yeah. Here's some beverage.
Okay.
Drink the beverage and tell me.
My sleep decoration's getting paid. I think it's Coke.
Oh, it's Pepsi.
Oh no!
I need. Does anyone else want to give it a go? Anyone want to take a bite out of the champ? I see a Tenfu. Wait, do you actually think you can do this? I have another shot. Come on.
Oh yeah, more. Oh, well, I got 3 more. No, 3 though. You can't help me.
Fresh cup. Turn around. Turn your back. Fresh cup. 1 peso. Okay, Ted, drink this beverage and tell me what it is.
Pepsi.
Oh, drink it all. One more test.
Stop giving him so much.
You have to do this really fast. It's like a 20-minute talk. Minus this time. Oh! There's Coke. I am not convinced that these two are. And does each volunteer, you guys can each take one of these for your travels.
Oh, thank you.
Okay. So that was an example of an interactive proof. I was interacting with these provers. I'm the verifier. For the rest of the talk, I'll call the verifier Merlin and the prover Arthur. Or sorry, other way around. Arthur's the verifier, and he'll ask questions to Merlin. And Merlin will just, Merlin has a tongue, so he can do computations that we can't. So the first element is laugh. I don't expect to make it in a cry, but if they do, I just want them to feel accepted and welcome. There's only one thing we're going to do in this talk, and we're just going to do it again and again and again. So if you don't get it the first time, hopefully you'll get it by the last time. We're just going to build up some complexity classes, and the smallest one is called P, and we're just going to keep adding things and getting bigger and bigger. Along the way, we'll answer 2 really important questions. One, what does randomness give you in computation? Kind of a weird question. And the second one is, what is quantum entanglement? There's a lot of bad answers to both of these questions. Interactive proofs are, in my opinion, the best answer to both of these questions. And complexity is only concerned with one math problem. That's all we need. The language problem. You fix a language out. This is a subset of binary strings, and they can be empty. And you fix a word x, And then we want to find out if x is an L or if it's not an L. Notice that we can't have an empty string, and L is allowed to be infinite. The strings themselves have to be finite, though. So here are some languages: binary strings beginning with a 0, binary strings that are palindromes, and binary strings that are primes. I've put down some numbers. Hopefully these are easy enough to recognize. But look at this one. The first one, we only need to check one bit. The second one, we might need to look at the whole string. And the third one, it's not even clear how to do this quickly. And if you've been to the cryptography talks, you'll know that primality testing and factoring is not the easiest thing to do computationally. And we can formalize this. This is our big idea. The whole complexity theory idea is that I'm going to group my languages by how easy a computer can decide them. If you know what a Turing machine is, we're going to track the time of a Turing machine. If not, just believe the strong church-Turing thesis, and then any computer will be polynomial equivalent to a Turing machine. And you can think of this as a Python program, a C program, a C++ program. Please don't think of it as a racket program. But here we go. First complexity class P. The languages that can be decided in polynomial time. So they take steps smaller than a polynomial. What is it a function of? The length of x. Another one is we don't have to use our time as a resource. We can use space. And I'm going to put space up here. And I'm putting, this is inclusion. So if I solve a problem if I can solve it in p space, I can definitely solve it in polynomial time. And the way to see this is that if I'm a polynomial, even if I write to memory at every single step, I can only take up polynomial memories. There's another one up here, isn't there? X. This is exponential time. So exactly the same thing as p, but you replace the time bound with exponentials. And they're included like that. If you can do something in exponential time, of course you can do it in polynomial time because these guys are slower. This inclusion is less obvious, and we don't even know if it's strict yet. This is quite embarrassing for complexity theory. We don't know if this inclusion is strict. It's believed that this is much, much larger than P, though. But we're garbage at complexity theory as a race. Another thing is, I want to ask, what if P has some help? So what if Arthur is able to get advice from Merlin? A classic example of this is primality testing. So if I want to check if something's composite, it could be really hard. I might have to look at all the factors. But what if Ted just gives me one of the factors, and then I only have to do one division? So you can see that if I have a certificate, if I have a friend, they might be able to help me do this. So checking L is something that you can do much faster. And we can also turn these guys into complexity classes. This is some other, just the formalism, is that if I want to check the X, it's an L, I'll just ask Merlin to produce me a certificate, and then I'll check my certificate, and if the verifier is actually good, then there should always be a certificate so that we can accept it, and that we shouldn't be able to be convinced by false certificates. These are called completeness and soundness, properties 1 and 2 at the bottom there, and if I say those words, that's what they mean. But the idea is now, I'm going to extend P again, but I'm going to say polynomial time verifier. So what does that mean? It means the certificate, I can check it in polynomial time. Like, if you give me a factor, I can check that it's in polynomial time. I'll put NP right here. I can also do it with an exponential time verifier right here. And there's a huge complexity class called RE. It stands for recursively enumerable. We don't really care what that means, but it's up here, things that have verifiers at all. And you might be asking, oh, what is out here? The halting problem, and the verifier for the halting problem is you just give me a transcript of the program. If you don't know what the halting problem is, it's just, for our language, we pick all programs, and for the yes instances, the X that are in the language, I'll just pick the ones that terminate, or that halt. And so we have all of these inclusions, and they make a really cool picture. But this is still kind of boring. We've only seen interaction with Coke and Pepsi. Why don't I see if I can extend NP again? The second one, we're going to extend NP, and we're going to allow you to do multiple certificates. So first, I'll ask a question. Merlin will give me an answer. I'll maybe check if the certificate's right, and then I'll ask another question, get another answer, ask another question, get another answer. Classic example is graph isomorphism. Hopefully, you've seen a lot of graphs, but they're just little drawings that look like this. You can see that these two graphs are not isomorphic because they don't have the same structure. Separate my graphs like this. But if you give me an isomorphism, I can check it in polynomial time. I just have to apply it at every vertex and check that the adjacencies remain the same. And you say, well, this isn't a very good interactive proof example because you only do one round. Whereas the interaction, this doesn't give us any more power. All of them can be phrased as one round. Deterministic interactive proofs don't really get us anything more. So I'm going to put DIP right down here. It's kind of a sad complexity class because the inventors wanted it to be much more powerful than NP because you can kind of keep questioning this person. But it's a pretty sad state of affairs. But we can extend DIP. This is another, just keep extending our complexity class by using randomness, like what I did with my coin. And now we don't need to accept deterministically, but we need to have a protocol that just accepts with probability 2/3 or 1/3. The constants aren't that important, except they have to be bounded away from 1/2. 1/2 above and 1/2 below. Now I'll probably get to the meat, why you came here, is that IP is probably, well, unproven, much larger than P, or much larger than DIP when you add randomness. And I'm going to do a Paul-style drawing of an interactive proof. Oh, I forgot to say the joke. I would like the prover to also be called Paul, but I don't get what I want either. So what is my language? I'll call it the language indexed by G naught, and it'll be all of the H's such that H is not isomorphic to G naught, and I want to check G1, is that an L? And I'm Arthur, and I know a Merlin who's really good at graphs, really quite a good friend at graphs. Someone like Joe or Taha who just absolutely knows their graphs. So what am I going to do as Arthur? I'm going to flip a coin. I'll call that C1. Just think of a peso. I'll pick a random isomorphism. Think of F1. Sampling a random permutation. I'm going to change the vertices around. And what am I going to do? I'm going to send to Merlin. That was scary. I almost wrote the wrong thing. The first, my isomorphism applied to a graph, either one of these two graphs, indexed by my coin flip. So half the time I'll do the graph that I'm trying to check, and half the time I'll check the graph that defines the whole language. And then Merlin is going to send back his guess for C1. And if Merlin sends me back the wrong thing, I know that Merlin cannot distinguish them. Because if the graphs were truly non-isomorphic, he could just look at all of the isomorphisms going backwards from this graph and check if they're equal to G1 or G2. So if he fails like the Pepsi test, then I'll fail him. If he gives me the right thing, I'm only convinced with probability 1/2. So I need to, of course, make another coin and make another isomorphism on Arthur's end and send them back to Merlin. And he'll send me another guess, G2. And I can do this until I'm satisfied. To fit this definition, I only need to do it twice, because that will get my, 1/4 is, a quarter is less than a third. Hopefully we're there. I'm going to do the same trick again. I'm going to extend the interactive proofs by adding multiple provers, and this is what people mean when they say multiprover interactive proof. The informal motivation is like, you're a police officer, two suspects are trying to convince you that they are not guilty of a crime, so I'm going to take them, I'm going to separate them a whole light year apart and ask them to answer questions within 1 day, so that I can ensure they're not communicating. Another example is if you're in like some kind of social deduction game, and there's two people who are trying to tell you that they're not a murderer, and you want to suss out, it's much better if you have two people to verify the story rather than just one. At least I would be happier if I said, oh, Ted didn't kill Maya because he was with Nick. And Nick says, yeah, I was with Ted. So that's why MIP, it was kind of unclear whether this was better or not, but the actual proof of the pudding was that MIP was much bigger. It was as big as NEXP, which is the languages that have exponential verifiers. Sorry for the jarring transition. There's another algebraic, or it's actually not algebraic, it's a mathematical object kind of on the same deepness as a graph. It's like just a bunch of sets and it doesn't have an operation on it. It's called the non-local game, and if you're a quantum fan, you may have heard of these. but we're going to build them up from scratch. Again, I'm Arthur. It's a multiprover proof. So there's Merlin and Gandalf, M and G now, and I'm going to kind of draw what they look like. Is that Arthur will, oh sorry, I should probably explain what this means. The Q's are sets of questions, the R's are sets of answers, or réponses for you French fans in the audience. Pi is a probability distribution on all the questions, and I just queried pi to get my question. And then A is Arthur. It decides whether the answers successfully answer the question. So Arthur will send to Gandalf and Merlin Gandalf's question, Q Gandalf, and Q Merlin to Merlin. Without talking, they're going to send questions, they're going to send their answers back to the prover, the verifier. Sorry. Oh, I messed it up even after changing them to Arthur and Merlin. They're going to send them back to, boom. So this is how the non-local games work. And you can see that it's an interactive proof, exactly the same as an interactive proof, but with 2 provers and 1 round of interaction. Kind of like a graph, you can ask questions about the graph, like what is the minimum number to color it. I'm going to say, what is my best strategy for winning this game? And omega C of G is the best classical strategy. Omega Q is the best quantum strategy. And what do I mean by a classical and quantum strategy? Classical strategy is just as they are here, and quantum strategy, they're allowed, the Gandalf and Merlin are allowed to share quantum entanglement. I told you I would successfully answer the question what entanglement is. That's still coming. What is a non-local game? Let's see the board. There's a very famous one called the Mermaid Parameters square game, and it has a square quite like this, something like this, some rows labeled by R, some columns labeled by C, some numbers at the end of the columns and some numbers at the end of the rows, and I want to fill this in with the numbers 1 and -1, so that if I multiply all the entries in a column or row, I get the number that's just outside of it. Well, I have to talk about the question sets and the answer sets. So the questions for Merlin, I'll make the rows. I hope this is big enough. The questions for Gandalf, I will make the columns, CJ, and I'll also write the probability distribution of any row and column is just uniform. It's as boring as possible. And A has to check 3 things. It has to check that the row multiplies to 1. It has to check that Gandalf's column multiplies to -1. And it also has to check that they agree. So if I give them this row and this column, this entry has to agree. A really simple strategy for this would be something as follows. I just put, I'll just fill this grid in with 1s and -1s. This one's a little hard to read. This is a -1, and and I can't actually fill in this one. So what you do here is Arthur, I'll give them each a question, and then if Alice gets this row, she'll say 1, 1, 1, and Bob will. Oh, I should have also specified the answer sets. They're just an assignment of the variables, is the answers. You multiply them, checking 3 things. You multiply these to make sure they're 1, you multiply these to make sure they're -1, and then you also have to check what's the same. And you can see in the strategy that they'll win unless they ask for the 3rd row and the 3rd column, but that will only happen 1/9 of the time. So they're going to win 8/9 of the time, and the sad story is that that's actually as good as you can do unless you share quantum entanglement, in which you can win every time. If you know anything about quantum mechanics, this is my proof. If you don't know anything about quantum mechanics, and you know something about linear algebra, the way to see that this is a winning strategy is that these are observables. You have to check that all the rows and columns commute, and you also have to check that they multiply to the identity through the rows and to negative identity through the columns. If you want to take products of matrices, feel free to do so. But we're ready to answer the question, what is quantum entanglement? And it might be the answer that might not make you happy, but this is actually kind of the best answer, is that quantum entanglement is what allows you to win this game. And this game in particular, if you've heard of a Bell test, this is completely equivalent to a Bell test. And if we discover some other physics that also allows you to win this game, I think they'll probably call it entanglement. But it just allows you to have correlated randomness. And this is how the randomness works to win this game. And finally, we can come back to. Are we okay on time? Oh, we're getting there though. We're going to extend MIP one more time, and we're going to allow them to share quantum entanglement. The text is not so important, but it just shows you that playing these games is exactly the same as doing the same proofs that we had before. And there's a problem. This is the name of a problem, and it's approximating within an epsilon the best quantum strategy for your non-local game. And that's as far as MIP star. And why are we talking about MIP star? Well, you might notice, because the drama is kind of leading there on this board, MIP star equals RE. And nobody wanted this to happen. People thought that MIP star would actually be weaker than MIP, because you're not giving the verifier a tool, you're giving the provers a tool. And a tool that they might be able to use to help them lie to you. Like if I had two Among Us imposters and they were lying to me, they could correlate their answers by measuring qubits. Like, how could this possibly give me more computational power? The answer to that is that the magic square game can actually only be won by that strategy I have up there. It's the only one that will do it. And so you're allowed to ask them questions that will force them to answer honestly or lose the game. So their desire to win the game will outweigh their desire to lie to you, hopefully. And if they really do want to convince you that something's an MIP star, they're able to do it. And how is this proved? Well, they solved the halting problem with an MIP star protocol. You define a non-local game that allows you to check if a computation ends, and you can check it in polynomial time. And it's kind of weird because this class is really small, the computations that they can do in polynomial time. And the kind of central question is, how much stuff can I give to someone so that they can do a really big computation still in polynomial time? And the P in MIP is polynomial. The verifier, Arthur, still runs in polynomial time, but they can check anything. No bound on time. They're not allowed to do that until they use quantum entanglement, which is kind of silly. Is anyone else confused? Yeah. That's it.
Do we have any questions?
James?
So at the beginning, when you were talking about DIP,
Yeah.
did you say that was a maybe equals?
Oh, no. DIP is provably equal to NP.
Oh, okay.
Yeah. It could also be P. Like I said, we're bad at these. Yeah, these inclusions, we don't know if they're strict. This one we know is strict. This is time hierarchy theorem. And I think that this one we know is strict as well. RE is massive. Laura?
Do we know if ESP and EXP are strict?
They can be made strict or not strict depending on oracle access. It's the same difficulty as P versus NP. So we don't know. Yeah, P versus NP, this famous problem, literal $1 million question. There's three main technical roadblocks to it, and it's the same with this problem. And one of them is called revitalization, and it's that these will be contextually equal to each other depending on how the oracle access works, depending on what provers. And the multiprover interactive proof system, or just interactive proofs in general, is the only proof system we have that is actually sensitive to oracle access. They've proved that you cannot prove P versus NP with a simple proof. It's a piece of jargon for proofs, but you need something like interactive proofs or stronger to tackle this question. Don't try it. You'll waste your time. It's very the other two technical roadblocks are still there. Taha.
Does there exist a multiplayer version of this?
Yeah, with more more
Yes.
of these guys.
Yeah.
Yes, you can actually do them with polynomially many of them, except you only need 2. Like having 3 is just as strong as 2, having n is just as strong as having 2, having n squared is just as good as 2. So that's why we only talk about 2. And you can also do more RAMs, but here it is. MIP is equal to MIP with 2 provers and 1 round of interaction. So this is all you need, and that's why we kind of switched to non-local games. Oh, there's some things on my French talk summary that weren't in my actual talk. QIP is the same as IP, but with quantum information. Same as MIP, but with quantum information. And this is, so you know how interactive proofs was like 2/3 and 1/3? So you only need to find it within an epsilon. If you find it exactly, it's in a class that's strictly harder than RE. And it's kind of weird to think about classes that are strictly harder than RE, because below RE and co-RE is everything that's computable and has an algorithm. In RE, these things are called semi-algorithms because they only terminate on yes instances. But these ones, we have no guarantees on them. Sorry, I don't know your name.
Sigma 1 and pi 2.
Oh, sigma 1 and pi 2. So sigma 1 is another way to say RE, and pi 2 is another way to say sigma 1 with some more things. So if we were in R, we could check is phi true for some really complicated phi's. Sigma 1 is there exists x such that phi of x is true. It's these types of questions. And pi 2 is for all x, there exists a y such that phi of xy. And it's pretty easy to see that sigma 1 is equal to RE, because again, you can use the halting problem. So like, to make my Boolean formula, I'll just say, does my program x terminate after, does my program P terminate after x steps? And then you can also go back the other way, it's exactly the same. Does that answer the question of what sigma 1 and pi 2 are? And the reason that these aren't all just in R is that these formulas are unbounded. Like it's not a good programming problem. What questions?
Actually, you don't have time.
No time.
But yeah, so if you have any questions, I mean, you're welcome to ask them, I guess. But,